Hi everyone. This video is a continuation of the previous one on two-level multi-level regression, and we're using the Jamovi program. In my previous video I went over the data characteristics. For our example, we basically had students who were nested within schools, and what we were trying to do is to predict student math achievement as a function of student level and school level predictors. Our first model, we tested an unconditional or null model in order to determine whether or not it was necessary to utilize multi-level regression as opposed to a single level regression, and we did find evidence of substantial clustering of observations within groups. So then we moved to step 2, which was testing a level 1 predictor, which was student socioeconomic status, and we found that socioeconomic status was a significant positive predictor of their math achievement. In the third model, we added in a contextual predictor, which was school mean SES, so basically taking the average SES across students and modeling that as a predictor of the variation in intercepts. And as I noted before, the intercepts are basically the school means for math achievement, just conditional on the presence of that level 1 predictor SES. And we found that mean SES was a significant predictor of math achievement. So in this model we're going to continue on by adding in 2 additional predictors, school type and school size. So basically our level 1 equation that you see right here is exactly the same as what we had before, and our level 2 equation for the fixed effect of SES is exactly the same. But now we're going to add in school type right here and school size. School type is basically a binary variable coded 0 for public school and 1 for private school, and then size is the number of students within a school. So now you'll notice that we have our gamma 01 for mean SES, we have gamma 02 for the regression slope or the fixed effect for school type, and then gamma 03 for the fixed effect for school size. So now let's go ahead and run our model using Jamovi. So going back, what we're going to do is we're going to move our we have mean SES and SES already included, so we're going to move the size variable down to the covariance box, and we're going to also add in school type as a factor. So let me note that because school type is already actually dummy coded, and because it's a binary variable, we could have just included it under the covariance box, but I wanted to show you the factors option, so that's why I'm using this instead of just entering it as a covariate. The factors box is really most relevant or most useful when you have a predictor variable that is categorical with more than 2 levels. So if you have a binary predictor, you could either enter it as a covariate or into the factors box, but if you have a factor variable with more than 2 levels, then you would definitely have to enter it as a factor if you're not planning on dummy coding the original factor variable and then including it those new dummy variables as covariates. So as we scroll down, let me just note too that as we add in our predictors, you'll notice that we don't actually have to explicitly move these variables from the left over to the right, because as we added them in above, they're it's populating under model terms. Scrolling down a little bit further, just note that as I said before, there are certain defaults in Jamovi. The default is to grand mean center, and so in this case you'll see that it tried to grand mean center the size variable at level 2. So I'm going to actually reset this to none, and under factor codings basically we have to decide on how we want to code it, and Jamovi will essentially do that for us. So I'm going to set this as dummy coded right here. So now when we do this, we get our output, and so let's just kind of walk through it. So I'm going to scroll down, specifically focusing on the fixed effects. So there's our fixed effects parameter estimates. This is the grand mean of the intercepts as we've talked about before. You'll notice that the mean SES variable is there's a positive coefficient, and we have significance. So basically mean school SES was a positive and significant predictor of the variation in intercepts, or basically the variation in the means on math achievement across the schools. Our level 1 predictor socioeconomic status is we have a positive coefficient, and we have significance indicating that students who scored higher on SES also tended to perform better with respect to math achievement scores. The size variable, you can see it's positive, but it's not significant at the conventional 0.05 level, so I'm not going to bother interpreting that. And then with respect to the school type variable, you can see that there's a positive coefficient. Remember, the coding is 0 for public school and 1 for private school. So the positive value is essentially indicating that students in the private schools did better on average than those in the public schools, and that coefficient is statistically significant. Under random components, you will notice that the variance for the intercepts has decreased, whereas the variance in level 1 really hasn't decreased any. You will notice that the ICC has also decreased a bit. When we look at the the test of the variance component for the intercepts, you can see that we have statistical significance. So there remains variation to be explained in the intercepts. Once again, we can talk about the reduction in variance in terms of percentage reduction. And so essentially our model 1 in this particular case is our previous model with just SES and mean SES, and model 2 is including all of those predictors at level 2 that we talked about. So for the first to test for the reduction or compute a reduction in variance at level 2, we're just taking the difference between the variance of the intercepts from model 1 and our current model, and then dividing that difference by the variance for the original model, and you can see it's 0.13. So there's about a 13% reduction in variance between groups. With respect to the proportion reduction at level 1 is basically 0. So adding in the predictors at level 2 did result in some decrease in the variance in the intercepts, but not a whole lot, and it certainly didn't have any effect with respect to reducing variance at level 1. And you'll also notice that the ICC really didn't decrease a whole lot by adding in those additional predictors. So now let's add in a randomly varying slope for SES. So it may be the case that the relationship between SES and math achievement at level 1 varies across schools, and so if we wanted to model that, then we can go back to our equation where we have the fixed effect for SES. This is our gamma 10, and then add in that mu 1j that I was mentioning earlier. So essentially this specification treats the treats the slope for SES as randomly varying across groups. And if we find that there is significant variation in the slopes, then the next logical question is, well, what types of school level factors might predict that variation? And that's where we jump off into modeling cross-level interactions. Now, it is important to note that in this particular case, because we're allowing the slope to randomly vary, then we will also have a variance term for the slope. So essentially, we've already talked about the variance of the intercept, so we laid it out as sigma squared subscripted mu 0j right there, and then we could also have the same for the slope, so we could say sigma squared mu 1j for the variance in the slopes, and then potentially we could have a covariation between the intercepts and slopes. So in this particular situation, then we have to think about how we want to model the variance components at level 2. Do we want to just estimate the variances of the intercepts and slopes by themselves and leave the covariance at 0, or do we want to allow there to be a covariance between those random coefficients? So we have two options that are available in Jamovi. One option is to basically specify a diagonal variance-covariance matrix, and what that means is that we are estimating the variance of the intercepts, and I'm using Heck et al.'s notation in this particular case instead of the mu 0j and mu 1j's that I've used up here. So with the diagonal matrix, do we want to, we're essentially stating that we're estimating the variance of the intercepts and the variance of the slopes, and the off diagonals are 0, specifying that we are essentially fixing that relationship between those two random coefficients to 0. So we're not allowing them to covary. An unstructured matrix, variance covariance matrix, is specified by using the correlated option under effects correlation. And so in this case we're estimating 3 parameters instead of 2. So in this case we are estimating 2 two parameters at level 2, which is the variance of the intercepts and variance of the slopes. If we specify an unstructured matrix, then we are estimating 3 parameters in this case: the intercept, the slope, and then the covariance between the two. So for our example, first off, I'm going to go up here to where it says random effects, and I'm going to select SES with school ID here, and I'm going to move this over to the random coefficients box. So now we are allowing both the intercept and the slope to randomly vary, and then the effects correlation that you see in this section of the screen, we have the option of allowing, basically setting our variance covariance at level 2, the matrix as either being correlated or uncorrelated, or basically a diagonal matrix or an unstructured matrix. Now by default it's going to set it as correlated, but obviously you can change it to not correlated. And just really quickly, even though I set it as not correlated in the PowerPoint, let me just show you what this looks like if we have it as correlated. So in this case you would have the variance component for the intercept, variance at level 2 for SES, and then so that's for the slope, and then you also have the level 1 residual variance. Down here you can see with random parameters correlation, this is the correlation between the intercepts and slopes, and so we could theoretically allow that to be non-zero if we wanted to. But again, for the purposes of the presentation, I just set it at non-correlated to have a diagonal variance covariance matrix at level 2. And so when we do this, kind of scrolling down, you'll see that we still have a variance estimate for the intercept and the slope, but now we also have a likelihood ratio test of the variance of the slopes, and you can see it's statistically significant, which is an indication that now we might be interested in determining whether there are level 2 predictors of the variation in that particular slope. And basically all of our previous regression coefficients, the interpretations are largely the same as what we had before. Basically student SES is a significant positive predictor of math achievement, and school level mean SES is a predictor of variation in the intercepts. School type, we also saw that is significant, where basically students in private schools are basically the mean for private schools is greater than the mean for public schools. And then we found that basically the size variable is not a significant predictor. So next we're going to test a cross-level interaction, and for this one we're going to keep it simple. We're just going to add in one predictor at a time. I could theoretically add in multiple predictors of the slope, and this is the slope right here, and now we're adding in mean SES as a predictor of the variation in the slopes. And so when we do this through substitution into our original level 1 model, if we substitute the level 2 equations into the first model, then you can see that now we would capture a cross-level interaction between the level 2 predictor mean SES and the level 1 predictor student SES. The decision not to include all of them was in part because by doing so the model would not converge. So I'm just basically going to enter, kind of provide a couple of demonstrations just to show you how to create and test for interactions across levels. So what we'll do is we'll scroll up to fixed effects, and what we'll next highlight, I'm going to highlight the SES variable and the mean SES variable, and then move it over to the model terms box. So when I do this, you'll now see that we have an interaction term that is presented. So this is the interaction term right here. So this is essentially modeling mean SES by SES, and so in this particular model, I'm essentially going to be treating mean SES as a moderator of the level 1 predictive relationship. There's the regression slope for the interaction term, and you can see that it's not statistically significant, and that's basically an indication that mean SES would not be considered a moderator of the SES math achievements relationship at level 1. Nevertheless, if it had been significant, we would most likely want to probe that interaction to sort of describe what's going on. So just in the interest of demonstrating that set of options in Jamovi, I'm going to scroll down to where it says plots and simple effects down here. So what I'll do first, I want to plot out the SES relationship at different levels of mean SES. So I'm going to move SES, my level 1 variable, to the horizontal axis box, and mean SES to the separate lines. And so now what you'll see when we scroll down a little bit, you'll see the plot of the simple slopes. And you can see that we're essentially plotting a simple slope at mean SES minus 1 standard deviation at the mean of that variable, and then also at 1 standard deviation above the mean for that particular variable. And you'll notice that the slopes are essentially parallel, and this is an indication, or this is further indication, that essentially there's no interaction that's taking place. If there had been an interaction, what we would expect is that the slopes of these lines would not be parallel, but that they would obviously be non-parallel. So in this case, you see that the relationship between SES and math achievement is pretty much the same across levels of mean SES variable at level 2. If we wanted to test those, if there were differences in the slopes, we had found that there was a significant interaction term, then we could also test the slopes themselves for statistical significance by going down to simple effects and moving SES to the simple effects variable box and mean SES to the moderator box. And so in this case, you would see then that our output would include the simple effects test. So now you've got the regression slope between SES and math achievement at 1 standard deviation below the mean on our moderator, which is our mean SES variable, and you can see it's significant. And then at the mean of our moderator, it's 2.2, is significant obviously, and then at plus 1 standard deviation above the mean on our moderator, and it's positive and significant as well. But notice that these slopes are essentially all the same, which is what you would expect, and that's what's being mirrored down here with respect to our parallel regression lines. So obviously there's no interaction that is taking place in this particular situation. Now, so let's try a different model. Let's take this out, and let's look at whether or not school type might moderate the effect of SES on math achievement. So I can do this by essentially highlighting SES and school type and then moving this over. So now I've got the interaction term up above right here, and you can see that the interaction between school type and SES, that's our school type by SES interaction term, you can see that it's statistically significant. There's our regression slope for the interaction term. And so now we would want to plot this out and perhaps test our simple slopes. So I'm going to go back down to the plots option, and I'm going to move mean SES off of this line, and I'm going to move school type to the separate lines to plot this out. So you can then, in addition, I'm going to go down to simple slopes. I'm going to move this off right here and move school type onto the moderator line right there. So now what you'll see in our output is the two regression lines for the regression line for each school. So you can remember that school type, the blue, the 0 right here is for public school, 1 is for private school, and you can see that the slope for public school is much more prominently positive than it is for the private school. So essentially the relationship between SES and math achievement appears to be more positive in the school public school context as opposed to the private school context. If we want to look at the simple effects test, you can see that the slope within the public school is 2.77 and is significant. In the private school, it's 1.45. It's also significant, but again, you can see visually that the lines are clearly not parallel, and again that the slope is more positive in the public school as opposed to the private school circumstance. So I do want to point out, let's just see what happens if I move the school type variable down to the covariance box. If we do this, you'll notice that with respect to our interaction term, it's still there. It's the same coefficient, still statistically significant. Now if we go down and we look at our plot and our simple effects test, now you'll notice that we have 3 regression lines down here in our plot, and then 3 levels of our moderator where the simple slopes are being tested. And that's basically because you're essentially, what's going on is we're taking that school type variable and essentially mean centering it. So at the mean would be 0, and then essentially you would have deviation below and above, and so that doesn't really make necessarily a whole lot of sense intuitively, but this is essentially what would happen if we tried to include the school type variable as a covariate instead of a factor variable. It's not wrong per se, it's just that the output with respect to the simple slopes and probing the simple slopes may be a little bit less intuitive than what we had before. So at any rate, that pretty well concludes this demonstration. Let me note in the PowerPoint, if you haven't already downloaded it, be sure to do so. At the very end of the PowerPoint, I do talk a little bit about mean centering and some of those issues. And there is a reference page at the back of the PowerPoint as well that gives you an idea about some different sources to consult. So that pretty well concludes everything, and I appreciate you watching.